Hi everyone. Today's lesson is about the logistic growth model. So this is an example of a differential equation. Here it's written in terms of y, sometimes it's written in terms of p for population because it's usually population growth. Now if we look here, we have dy dt equals k times y. We've seen that before, and solving that part of the equation would lead to exponential growth. But we have this extra factor here, m minus y. M is the maximum population that the environment can sustain. So as y increases, as the exponential growth takes over, then the difference between m and y becomes smaller and smaller, and eventually that factor will flatten out the growth. Now, let's take a look and see how this would work. So let's write our equation dp dt, p for population, equals some growth constant k multiplied by p, and then m minus p. M is the maximum population that the environment can sustain. So to solve this, we would separate variables first. dp over p by m minus p would equal k dt, and we would integrate both sides. The left-hand side of this equation, we would have to, let's just do an aside, we would have to use partial fractions. So we would say we have 1 over p by m minus p. We'll define this as a constant a over p plus a different constant b over m minus p. Now, combining these two terms, we would have a times m minus a times p plus bp, and that am that's a constant a, which we don't know yet, and m is maximum, so that's a constant. We would have over here b minus a times p over p by m minus p. Now remember, all of that equaled, well, the constant was 1 and there was 0 term involving p, the variable. So let's take a look at the correspondence here. The constant 1 equals a times m, and the coefficient 0 in front of our pronumeral equals b minus a. Writing this to the side here, we would get our, let's see, what does this imply? It implies that am equals 1, so a equals 1 over m. Furthermore, we could see from the green highlight that b minus a equals 0. So b is the same as a, which we already knew was 1 over m. Now that's going to be, what we'll do, of course, is we'll go back to where we started there from equation 1. Now equation 1 originally said dp over p by m minus p equal the integral of k dt. Now we won't write this, we'll write this as 1 over m over p and 1 over m on m take p. All of that is integrated with respect to p, and that's the integral of k dt. So let's integrate now. I'd have 1 over m by the natural log of m. I beg your pardon, that's a p in there. Plus, we would have 1 over m by the natural log of m minus p. Now the derivative of m minus p is -1. Dividing by -1 means just that that term becomes negative. And that would equal k multiplied by t plus an arbitrary constant of integration. Let's multiply both sides by this m. So I would have k by m by t, and then m as a constant by c is just a new constant of integration. The left-hand side then, I would still have the ln of p here minus the ln of this bit, because I multiplied by positive m. So this would be the ln of p over m minus p. Writing this using exponents, p over m minus p would equal e to the power of k m t plus c1. Now multiplying by, or adding c1 there, that's equivalent, of course, to multiplying by e to the power of c1. But really, e is a constant, c1 is a constant. I could simplify my work if I just define this as some different constant a. This might be an opportune time to evaluate. So at t equals 0, we would normally say that the population is p0. Let's substitute. I would say p0 over m, the maximum carrying capacity, subtract p0 equals the unknown factor a. Now e to the power of k times m times, well, t is 0, so that's e to the power 0, which is really just 1, which means that I've evaluated my constant a. It's p0 over m take p0. Now that's a handy little thing for future, but I'm going to keep working with a in my equation because it's easier and it's more compact. All we need to do now is isolate p. So let's have p here, multiplying the m minus p to the other side. I would have m by a by e to the k by m by t minus p times a times e to the k m t. So on the other side here I would have p plus p by a by e to the k m t equals m by a e to the k m t. Now I'm going to factor p, so this is really 1 plus all of those parts there. So p then is m by a by e to the k m t over 1 plus a by e to the k m t. Now we could stop there, but it's a little bit messy to have pronumeral t in the numerator and the denominator. It works, but we can tidy this up with a, oh, what's that down there? Something left over from previous. So it is a little trick that we can use to multiply by e to the negative k m t in the numerator and e to the negative k m t in the denominator. So what do we get? Well, this first, the numerator would become m times a, because by the time we add this to this, it's e to the 0. Of course, the denominator here, oh, I've got more rubbish down there somewhere. I don't know where all that came from. The denominator, well, e to the negative kt times 1. Right, let's multiply by this part first. We would get a, then we would have plus, that times 1 is e to the negative k m t. There's my solution to the logistic growth model. Remember, we had from earlier that a equaled p0 over m take p0. That's the original population, p0, and m is the maximum carrying capacity. Let's have a quick look at this in action. So here is a logistic growth model. Now I've drawn the slope field for the differential equation in the background, and the green equation is the logistic model that we just solved using p0 of 1. So there we are, we can see that when time is 0, the population is 1, with maximum of, well, 10.1 doesn't seem right, maximum of 10. Go on, stop on 10. So there's our maximum value of 10, and a growth factor of 0.05. As you can see, originally the graph tends to rise rapidly like an exponential does. But as the difference between the population, so the population is now approaching 6. The difference between the maximum and 6 is now 4, so it limits the growth. And then eventually, as the difference between them gets very, very small, it flattens out the curve. Oh, where have we heard that phrase before? Now, this growth factor K is very sensitive. Look at a K of 0, well, the population stays flat. That's exactly what they're talking about with the spread of this virus at the moment. They really want the transmission. K represents the transmission rate between different people. They really want that to drop down as low as possible so that it stays flat. It doesn't spread. But if K is, I'll just increase that a little bit. If K increases, well, that's if we don't have social distancing, and that's if we have people not practicing, hand hygiene. So you can see that it grows very rapidly. And this is what was happening at the beginning of 2020, when there was not a lot of social distancing and there was free travel between international countries and so forth. So with all of the current restrictions that we've got, the transmission rate has dropped. And that's more or less the sort of graph that you see when you look at the news and they're reporting the number of cases. That's it for the logistics model. Remember that it starts with that differential equation there, and it ends up being that solution there. Okay, thanks for watching.